Hi all. Today we discuss the coordinates of a particular vector in a vector space relative to two distinct bases of that vector space. We know that there are more than one basis for a vector space. Say, if we consider R2, then we have a standard basis that is 1 0 0 1. So this is one of the basis of R2, R cross R. We call this as some B1, or we write this as some C. This is basis C. It's a subset of R2 anyway. This is R2, and we can define another basis, say D, consisting of the vectors this minus 1 1 and minus 1 1 minus 1. Okay, this is another basis vectors of the same R2. We know that if we have a vector, say V, then this V can be written as a linear combination of the basis elements of the C as well as the basis elements of this D. So when you write this V, say we call this V as some 7 comma 2, then this 7 comma 2 can be written as 7 times 1 0 plus 2 times 0 1. So this expression will give the basis of V with respect to C. So that is nothing but the coordinates, the coefficients of or scalar of these expression. So that is 7 2. So which gives the coordinates of this V relative to the basis C. The similar way we can write the same V as a linear combination of this 1 1 and minus 1. Okay, how you write this 7 2 as a linear combination of this? That can be written as 9 by 2 times this 1 1 plus 5 by 2 times 1 minus 1. Okay, when you add this, you can get the first term as 9 by 2 plus 5 by 2, that is 14 by 2, that is equal to 7 here, and we have 9 by 2 minus 5 by 2, that is 4 by 2, that is equal to 2. So the same V can be expressed as a linear combination of these vectors. These are the basis vectors of D. Then the same V, the coordinates of same V relative to the basis D is nothing but the same V can be written as this form, and the coordinates of the same V relative to another basis D as we can write it as 9 by 2 comma 5 by 2. This is the matrix, and this shows that the same particular V can be expressed, a particular V may have two different or more than one different coordinates relative to or depending on these bases. So which shows that naturally we can ask a question, can we connect these two? Okay, is there any relation between the coordinates of the same V, we are not changing this V, relative to two distinct bases of a given vector space? That is, we have to prove in the next theorem. This theorem gives the idea or relation connecting two distinct coordinates of a particular V corresponding to two different bases. So this is a statement: if VC and VD are the n-tuple or coordinate representation of a vector, a single vector, a particular vector V, with respect to the bases C and D respectively. So these are two distinct bases of a vector space V, and Pj, P is a matrix with Pj is the n-tuple representation of the jth basis vector in C with respect to the D basis. Okay, then this Vd is the coordinates of V relative to the basis D is equal to P times, P is the matrix obtained by connecting the basis elements in C and basis elements in D then that can be written as Vd, the coordinates of V relative to the basis D is equal to P times the matrix times the coordinates of V relative to the basis C. Okay, so this matrix is obtained by getting writing this Pj as the jth column of that matrix. Okay, so this is what we have to prove. So for the proof, we write C consisting of the vectors. This of proof. Let C, the basis C consisting of the vectors u1 etc un. We are assuming that this C and D are the basis for the same vector space. Then this D can also consisting of the vectors n vectors, say v1 v2 etc vn. Okay, so these are the vectors in D, and we will write any C as a linear any V as a linear combination of this u1 u2 etc un. So we write an arbitrary V. So by fixing this V, you can write this is C1 times u1 plus etc Cn times un, or you write the summation notation summation j is equal to 1 to n Cj uj. So when you write j is equal to 1 to n, you can get this expression. Okay, so this is the from this you can write the coordinates of V relative to the basis C, and it is denoted by this symbol, that is nothing but the scalars C1 etc Cn. So this is the coordinates of V relative to the basis C. Similarly, if we have the same V, we can write this V as a linear combination of this v1 v2 etc vn as well, because that is also basis of the same vector space. So we write that scalars as d1 v1 plus etc dn vn, because it's consisting of the same number of elements. So using summation notation, you can write this is equal to I equal to 1 to n this di vi. Okay, so this is the from this expression you can write the coordinates of V relative to the basis D consisting of the vectors v1 v2 etc v, and that is equal to matrix d1 etc dn. So this is the representations of V related to two distinct bases. Consequently, you can get the matrix of or coordinates of this V corresponding to two different bases. Okay, now we write this is the corresponding to the basis C, and this is the coordinates corresponding to D. Okay, now we have to connect these two coordinates relative to using some matrix. Okay, so since this u1 is an element of, if we take a u1 is an element of V, and this is a basis, then this u1 can also be written as a linear combination of v1 v2 etc vn as well. So that is the scalars. I'll write the scalars corresponding to u1 as p11 v1 plus p21. Please note this is 1 1 and this is 2 1, because this is going to be the first column of that matrix P in the theorem. So we write this is p11 v1 p21 v2 plus etc pn1 vn. Okay, so you can write it as this form, and if you take u2, then that will give p12 v2 rather than this instead of writing p21 here, we write p12. This is because these scalars are going to constitute the second column. So we write it as p22 v2 plus etc etc plus pn2 vn. And similarly, we can write this, any un can be written as p this is here 2 here for u2, and here we have 1 here for u1, and for n we have p1n v1 plus p2n v2 plus etc etc pnn vn. So this is the last case. So in between we have a number of expressions are there. So if you write a general expression, say uj this uj can be written as what is the expression for uj? Analogous to this, you write uj as p1j v1 plus etc. This is p2j v2 plus etc. plus pnj vn. So this is the expression for uj in general. So we write this as a this is in the summation form. Summation, this is the summation I equal to 1 to n, I equal to 1 to n pij, this is for uj, so pij vi. Okay, that means if you expand this I for I equal to 1, we have p1j v1, and I equal to 2, we have p2j v2, and so on. So this is the general expression for uj. Okay, now we have to connect these two things, the basis, the coordinates of v related to c and coordinate of v related to d. In order to connect those two quantities, we write that u1 from this you can write this, what is the coordinates of u1 relative to the basis d, because these v1 v2 vn are elements of d. We write from this expression, you can write what is the matrix of u1. Matrix of u1 relative to the basis d is nothing but p11 etc etc pn1. So this will give these coefficient will give the coordinates of u1 relative to the basis d. Okay, similarly the coordinate of u2 relative to the basis d is p12 etc etc pn2. Okay, so this is the coordinate of d, this u2 relative to the basis d. Similarly you can write u1, what is the coordinate of un, that is obtained using this expression or these coefficients p1n etc etc pnn relative to the basis d. Okay, so using these coefficients you can construct a matrix say p, so that consisting of the elements p11 p12 etc. So we defined a matrix p, and it is denoted by the matrix p relative to c and d. Okay, this matrix consisting of the elements, these are the elements p11 p12 etc p1n. On the other way we can write this is the first column p11 p1 p21 etc. This is the first column pn2. So the first column is obtained from this expression. This is the first column is the coefficient, these coordinates of u1 relative to the basis d. Similarly the second column will be the coordinates of u2 relative to the basis d. So this is n, this will be, this is n1 and this is n2 and so on. So the last one will be p2n etc etc pnn. So this will be that matrix. If you define a p in this manner, then you can write any v can be expressed as the summation j is equal to 1 to n cj uj, that is equal to, this is the expression of v with respect to the basis elements uj, and we substitute for this uj, that is equal to summation, we read that as summation j is equal to 1 to n cj, and substitute for this uj from this expression. Uj is this one, uj is equal to summation I is equal to 1 to n pij vi. Okay, so this is the expression for this uj, but we know that this cj is independent of this I, this summation is depending only on I. So you can write it as summation j is equal to 1 to n and summation I is equal to 1 to n cj pij vi. That means you can take this cj inside, okay, and we write this expression by interchanging these two summations. By interchanging to summation we can get the different order of the summation, so that will make the sum as it is. So we write that doesn't make any change in the sum. So this I is equal to 1 to n summation j is equal to 1 to n. This can be written as p I j c j. Here this I is the first sum. Here we have vi, but we know that the first sum is depending only on j, so you can take that vi out. Okay, what is the meaning of this expression? What we have started is v as a linear combination of this uj, and finally we got an expression as a linear combination of vj or vi. Okay, so once you write this v as a linear combination of this vj, we call those elements as d1 v1 plus etc dn vn. So this will give the coordinates of v relative to v1 v2 etc, that is d1 d2 etc dn. Okay, but we know that we are considering the ordered basis, so corresponding to any ordered basis, these coefficients will be unique. Okay, so whenever you write this v as a linear combination of v1 v2 vn, then those coefficients will be same as these coefficients. That means when you put this I is equal to 1 here, then this expression will give the coefficient of v1. Similarly, if you put I is equal to 2 here, then from this expression you can get the coefficient of v2. So that must coincide with this one, because the coordinates these coordinates will be unique if this bases are ordered bases. So from this expression, this is the expression of v as a linear combination of elements of d. So these elements will give the coordinates. That means if you write this d1 d2 etc are the etc dn are the coordinates, then this will be the same as this one. Okay, when you put I is equal to 1 here, so that will be summation j is equal to 1 to n. In the place of I we have 1, that will be p1j cj, this will be the coefficient, and finally we have our dn, the last scalars will be corresponding to the case I is equal to n. So when we put I is equal to 1, then summation will be j is equal to 1 to n p n j cj. Okay, so these are the coefficient of this is nothing but the coefficient of v relative to the basis d, and that can be written as this form. Okay, but we know that this is nothing but the product of two matrices, say p11 etc. This is nothing but p11 c1 plus p12 c2 plus etc. So that is the first row, and finally we have pn1 c1 plus pn2 c2 plus etc. So then this can be split into product of two matrices, that is nothing but p11 p12 etc p11 into c1 c2 etc cn. So once you write this, then we can get this is same as this one, and we know that this is the matrix denoted by pcd. So we have this p relative to c and d times, this is that matrix, times what is c1 c2 cn. c1 c2 cn is nothing but the coefficient of v coordinates of v relative to the basis uj. So this is nothing but the coordinates of v relative to the basis c. So which shows that coordinates of any typical v relative to d can be written as the matrix p c d. This is the matrix obtained by considering the elements of the first basis as a linear combination of the elements of the second basis, and this times the matrix of this coordinates of c relative to the basis d. This is what you have to prove in the theorem. So we write this as the proof of the theorem. So please note this. In the textbook, the proof is discussed earlier, and after that the theorem is the statement of the theorem comes. So please note this proof of the theorem, and there are a number of examples are discussed, and later and in the next class we will consider the relation between or the properties of this p. Okay.